Our team works on cellular network speech enhancement and aims to improve speech transmitted over handheld devices via Google Meets. We will now detail our contributions, approach, and achievements. Speech quality is often affected by two factors: background noise and the transmission noise. Most literature currently focuses on removing background noise caused by being in a noisy environment. Our work goes one step further to remove transmission noise, which is added when speech is transmitted through a cellular network. In our work, we aim to outperform the current industry speech enhancement features provided by Google Meets for speech transmission over calls. Our contributions are twofold. First, we present a novel speech dataset synthesized with both background and transmission noise. Next, we introduce a custom loss, called tap loss, during training to outperform state-of-the-art speech enhancement models on our novel dataset. The speech data is synthesized as follows. A Google Meet session is started and we call into it using a phone. We play a noisy speech audio in Google Meets simulating the background noise. This audio that is relayed to the phone is then recorded, thereby capturing the transmission noise created in the relay process. Overall, we produce 400 training samples, which are 30 seconds each, and 150 test samples, which are 10 seconds each. Let's have a look at the two state-of-the-art models that we use as baselines in our work, demux and full subnet. In demux, the encoder transforms input audio into a latent representation that is passed to a decoder via a recurrent network. The decoder then produces the denoised audio. A skip connection connects the output of the ith layer of the encoder and the input of the ith layer of the decoder. The full subnet architecture consists of a full band unit that captures long-distance dependencies and a subband unit that attends to local spectral patterns. The audio is first passed to the full band unit, which consists of normalization, a recurrent network, and a final linear projection and activation layer. This output is concatenated with the original input and passed into the subband unit. The subband unit is similar to the full band, but does not have the final activation layer.
However, the current models suffer from common shortcomings. First, they are unable to improve pitch, perceptual quality of speech, and have non-differentiable losses, which makes optimization difficult. To combat this, we introduce a new loss: temporal acoustic parameter loss for speech enhancement, to improve speech perceptual quality and intelligibility. Tap loss is a differentiable estimator which calculates 25 low-level acoustic descriptors in 4 categories involving frequency, energy, spectral balance, and temporal parameters. We thus extend the existing loss to include tap loss, which results in increased perceptual quality and intelligibility. demux is prone to produce tonal artifacts in speech which are high-frequency buzzing noises. The STFT loss in demux further amplifies this issue since it involves calculations in the time-frequency domain rather than just in the time domain. Thus, we propose to modify the demux loss by reducing the weightage of the STFT loss. We perform an ablation study on our generated dataset to find the optimal values for each of the hyperparameters lambda1, lambda2 for demux, and gamma for full subnet. We compare model performance in 2 classes of metrics: speech quality and speech intelligibility. PESQ captures the human subjective rating of speech quality degradation caused by poor network conditions, whereas LLR assesses the goodness of fit between clean and enhanced speech. STOE is an intelligibility measure that measures how additive noise affects speech, whereas CSII measures the signal-to-noise ratio in separate frequency bands. Here are audio samples depicting the denoising of speech by the full subnet fine-tuned model.
She had your dark suit in greasy wash water all year.
She had your dark suit in greasy wash water all year. She had your dark suit in greasy wash. She had your dark suit in greasy wash water all year.
We outperform the demux and full subnet baselines. We further aim to increase our training data from 400 samples to 1200 samples in order to fine-tune each of our models. We believe that our work can find applications in the telecom industry and directly with mobile phone manufacturers. And also the obvious.